Go.
Hi AP Calculus students. Welcome to section 2.6. It is the last section of chapter 2.
Yes.
And it's a doozy. That's Brother Doug. Hi Douglas.
Hello.
Hi. It's related rates. This does, as you'll see way down here already, this takes some practice. And so we're gonna let's start practicing. So on number 1, we will now use the chain rule. Gonna stop. You use chain rule on implicit differentiation, right? You learned it in 2.4, used it in implicit differentiation in 2.5. Now we're also gonna use it in 2.6 because we're gonna have some time involved. We will now use the chain rule to find rates of change of 2 or more related variables with respect to time, because we know time is an independent variable and everything changes according to time. Here's some examples. As a radius of a circle grows constantly, we will call that dr dt, the derivative of the radius with respect to time, right? So the rate of change of the radius with respect to time. As a radius of a circle grows constantly, the area grows increasingly. So when the radius grows constantly, we find the area grows increasingly because it makes sense, and because the radius is being squared. When the area is changing, the rate of change of the area, we call that dA dt, the derivative of A with respect to time. Here's another example. As the height of a cone decreases, let's say you have this cone and the height is going downward. As the height of a cone decreases constantly, we call that dH dt, the rate of change of the height with respect to time. Its volume decreases faster. We call that dV dt, the rate of change of the volume with respect to time. At one point in time is a derivative. Okay. So when a height changes constantly, the volume actually decreases faster because of the squared component in it. These are called related rates. Of course, when one variable changes, it causes another variable to change, and they are related to each other. So how do you solve related rates problems? With a lot of practice, but here's some basic steps. A, label all quantities and rates in a picture if possible. So all information they give you, if you can, draw a picture, label everything. List all quantities and rates that need to be found. I usually write them and put a question mark. If you identify a rate, such as dV dt, dA dt, dH dt, dr dt, you must identify the variable or the quantity used in that rate. For example, if you have been given or asked for dr dt, the rate of change of the rate with respect to time, you have to label an R in the picture. If you use the letter R, you gotta have an actual R in your picture or in your equation. If you're trying to find dH dt, something has to be labeled H, okay? So B, write a primary equation relating the variables. No rates in there. We're just writing equations that we actually know, okay? C, this is more for 2.6b. There'll be an example video. If you have a variable in the primary equation you do not have information for, or you are not asked to solve for, you must use secondary information to substitute into the primary equation to eliminate this variable. Right? So if you have an H or a dH dt and you're not being asked for it, right, it has to go. It has to be replaced with something else. D, find the derivative of your primary equation with respect to time using the chain rule. So this is always with respect to time. So if you are taking the derivative of R in an equation with respect to time, that would be 1. The derivative of R is 1 times the derivative with respect to time. We call that dr dt. If you're taking the derivative of V, of volume, with respect to time, the derivative of V is 1 times the derivative of V, which is dV dt. E, substitute any given information into the derivative of the primary equation and solve for the rates asked for. This takes practice. So this is a lot going on here. To say this again really quickly, any quantities or rates you've been given, give them a list, give them a picture if you can, right? If you label a rate, you have to label the variable that you have in that rate. Write a primary equation. If there's anything in that primary equation you don't need, it's got to go using secondary information. Take the derivative of the equation, plug in the information that you have to find the information that you need. This takes practice. So for 1A, we won't be able to draw a picture on this problem, but it's a nice basic one. Here's what 1A says. Given y equals the square root of x and dx dt, the derivative of x with respect to time is 3, find dy dt, the derivative of y with respect to time when x equals 4. Okay, here's my primary equation. They gave it to me. I am going to take the derivative of this equation on both sides with respect to time. There we go. So this is dy dt. Again, I'll say this one last time here and here. The derivative of y is 1 times the derivative of the inside function, which is y. There's supposed to be a t there, so that would be times the derivative of y. So 1 dy dt equals the square root of x, its derivative, I kind of had you memorize, that's 1 over 2 square roots of x times dx dt. So you will always have, when you take the derivative, a multiplication of a rate with respect to time. One last time, we were taking the derivative with respect to time. We did, but there was an x in our equation, so we have to multiply it by the derivative of the inside function, which is dx dt. Okay, now, let's go back. They asked us to find dy dt. This is what I'm looking for. They told me that dx dt is 3. I need an eraser. They asked me for dy dt. I usually circle when x is 4 and dx dt is 3. There we go, and we get 3/4. That's your answer. Primary equation, took the derivative with respect to time, put in the information, solved for what I needed. Let's try 17A. So, I'm not going to write out 17A, but I am going to list the information. Of course, you are welcome to look in your book. A spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute. So this is a rate of inflation. Notice that this is a rate, I need to label it. We'll take a look here. This is a volume, right? Centimeters cubed. Volume per time. This is the rate of change of the volume over time. I will call that dV dt. Also, it's positive because this sphere is expanding. If the sphere were getting smaller, I would put a negative on that 800. Okay. Now, I just use this variable v. I don't see 1 anywhere. I need v, right? I know the volume of a sphere. Volume of a sphere is 4/3 pi r cubed. Let's keep reading. How fast is the radius of the balloon increasing? I'm going to call that dr dt. It says how fast is the radius increasing. That is a rate of change of the radius, and it's changing over time. I used an R, gotta have one. There it is in the picture, there it is in the equation. How fast is the radius of the balloon increasing? At the instant the radius is 30 centimeters when R equals 30. Okay, here's our primary equation right here, right? Let's see. I have a dVdt. My B is okay. They want dRdt. My R is okay. I believe I just need to take the derivative of this equation now with respect to time. Here we go. This is dVdt. This is a constant I'm going to keep. The derivative of r cubed is 3r squared. Don't forget, times dRdt. Chain rule. Okay, notice these 3's cancel out. All right, let's take a look here. I'm going to use a different color. It is time to pop in the information they gave us and solve for what they asked us for. Let's see. They gave us dVdt, 800 cubic centimeters per minute equals 4 pi. My r, they told me when r is 30. dRdt is what they're asking me for. I tend to circle it. There we go. This is 800 divided by, this is 900 times 4, 3600 pi equals dRdt. I'm pretty sure they reduced this. Let's see. Divide each by 4, 2 over 9 pi. And it's the rate of change of the radius with respect to time. Our measurement was in centimeters. Our time was in minutes. There's our final answer. Next, 33b. On 33b, they gave us a picture, so I will go ahead and draw it. Let's see. Here's the picture they gave on 33. A man 6 feet tall. Okay, I'm looking at the picture here. Here's what they gave me. Again, 33b. A man, here's a guy. Well, let's make him a guy. Hey. Oh, his feet gotta touch the ground. He's happy. He's walking. He's 6 feet tall. A man 6 feet tall walks at a rate of 5 feet per second away from a light. So here's a light that is 15 feet above the ground. So this light is 15 feet, this man is 6 feet. I'm gonna go back. A man 6 feet tall walks at a rate, okay, so he's walking of 5 feet per second away from a light. Got the arrow. That is 15 feet above the ground. Okay, they gave me this rate. I need to name it something, right? Here is the rate that this piece of information in the picture is changing. Since it's at the bottom, there's a lot of things I could call it. I'll call it B for base. So that means that this length is changing at a rate of dB dt, 5 feet per second. Because he's walking away and B is getting bigger, I'm going to keep this positive. If he was walking towards the light, I would make this negative because the actual length is getting smaller. When he is 10 feet from the base of the light, when B equals 10, at what rate is the length of his shadow changing? I'm going to write that out. At what rate is the length of his shadow changing? Interesting question. Okay, well, we have to find a shadow, right? This is his shadow right here, right? The light is coming over the top of him and his shadow's out in front. Let's call that S for his shadow. And they are asking us at what rate is the length of his shadow changing. They are asking us for ds dt. Okay, now what I need is a primary equation. Before, it was a sphere. We knew that equation. But here, what am I going to use for equation? The answer to this is a proportion. There's not an exact formula that you use, But what I see is I have a large right triangle and a small right triangle, and they are in proportion to each other, if you remember that from geometry. So let's take a look. Here's this large triangle in purple, and here's this small red triangle. And because these two lines are parallel, they're both vertical measures, the purple and the red triangle, if their proportions are in proportion, their sides are in proportion to each other. So what is my formula I'm going to write? Remember, no rates yet. I am going to say, let's see, this little red triangle, that its bottom compared to its height is equal to the bottom of the purple triangle compared to its height. Here's my equation. Now, I think I can do a little bit better than this though. Let's try cross multiplying. So that's 15s equals 6 times b plus 6 times s. Again, I haven't taken the derivative yet. I'm just trying to make this a little nicer to take the derivative of. Take a look. I can subtract a 6s from both sides. That would be 9s equals 6b. Let's see, I'm not sure if I want the b alone or the s, or I could take the derivative right now. But let's take a look. They're asking me for ds dt, so let's get that s alone. Let's divide by 9, and I get s equals 2/3 b. Okay, here is my primary equation. I am going to come to the left and take the derivative of it with respect to time. There we go. The derivative of s with respect to time is ds dt. That's what they asked us for. The derivative of, I'll keep my 2/3, and the derivative of b with respect to time is db dt. There we go. They asked us for ds dt. Hopefully they gave me db dt. They did. It's 5. So the rate that his shadow is changing is 2/3 times 5 equals 10/3. And what were our units? Feet per second. Notice they did give me before, when b is 10, I did not need it. There we go. There's your first practice, and I hope you end up enjoying section 2.6.
Have a great weekend.
Yay!